there, on there. Okay, so this is supposed to be a mini course to introduce the subject and sort of build up to something more modern at the end of the rigorous stuff that's going on. So my plan is the first 2 lectures, or maybe 1.5 lectures, is to introduce the main concepts of how you go about things. And in the last lecture, maybe a little bit before, I want to, all this technology that David and others have developed, right? I want to give some version of it, and how you use that technology to prove, for example, the existence of a non-trivial fixed point. Okay? But first, my considerations will be quite general. I mean, not general, but specific, simple, and some approximate calculations which give us an idea of what this is all about. Okay? Okay, so let's see. Okay, so I have some general balatin, as they say, first of the stuff. So this gives more or less a program. Something getting cutting off. Okay, so Dirac, who was here, always said you must have cutoffs. You have to have an ultraviolet cutoff, a cutoff, a volume cutoff. You should solve the equations and then take limits. That was his. That's what the singular stochastic partial differential people are doing actually. They are putting in cutoffs, they're solving the equations, and they're taking limits. Okay. So this is very much a Dirac's program. But historically, another program that started off was due to Ken Wilson. There was a lot going on before Ken Wilson, and that's known as the perturbative renormalization group, in which you first prove the renormalizability, perturbative renormalizability of a theory, then expand it out, assume it makes sense, and get some scaling relations from that, known as the Gell-Mann-Low relations or the Callan-Szymanczyk relations. And then from this, a large amount of work was done, and interesting evidence was uncovered. But Wilson said, well, all this is perturbative. We don't know the series diverges. In bosonic field theories, the series diverge. Okay? Even for the anharmonic oscillator, the series diverges. It's Borel-Somerville, but diverges. So let's put in a cutoff as necessary to define something, and let us try to take limits, have some procedure to take the cutoffs away. So this is what Dirac said. So that's what I say, that the cutoff functional integral solves, you can derive the cutoff equation of motion from the cutoff functional integral, okay? And he's going to make an analysis of this renormalization group flow, which he defines, which I will come to in a minute. And no infinities are ever met in this procedure, okay? And instead, the problem is converted into one of a dynamical system, which will come to that. Okay? Let's see. So, the most important point, that Wilson came into the subject from field theory, not from statistical mechanics. And he was asked to explain by his colleagues in Cornell what various things were going on about critical phenomena. The critical exponents had been realized earlier by Michael Fisher. There was a big group in King's College London which was doing numerical computations and the high temperature computation. And as you approach a critical point, which I'll define, these things diverge. So Michael Fisher said, a famous article, 1967 Reports on Progress in Physics, I think. He said, let's fit algebraic expressions. And from that, to fit in the algebraic expressions, the high temperature expansion, as you go to the critical point, these things will diverge, but we'll measure how they diverge. Okay? So that was all right. Then the scaling things came along with using the renormalization group, And then Giorgio de Castro, for example, and other people, okay, contributed, but none of them had a very computational scheme until the epsilon expansion came along. So, anyway, so I won't go into all that. I just wanted to mention a little bit of history. It's very long, as you can see. So the idea is I will be concentrating on critical theory, then I'll explain what I mean by that through approximate calculations, and produce scale invariant field theories, okay, via scaling limit. Okay. Of course, secondly, for simplicity, I'm going to work in the continuum. After all, the SSPD people work in the continuum, although recently Martina and Masvidal have worked on the lattice, right? And I'll work in the continuum and in finite volume, okay? The idea is I want to take the continuum limit in finite volume. The volume is going to be a torus, and in some way I'm going to introduce a cutoff, okay? And how do I get rid of that cutoff? That's a problem. Okay. So lattice versions are available, and I'll give references. I haven't compiled a full list of references yet, but I will on each topic. I'll give a list of references which will be part of the show. Okay, so the first two lectures I'll be introducing the essential ingredients and some approximate picture. I'll be calculating some approximate flows, okay, from which you'll see a lot. And the last lecture I'll give something more rigorous, okay? So I haven't put too much in a frame, David.
No.
Right?
Okay.
And you stop me if I'm going too fast. Okay? So I said 5 minutes per frame. That's reasonable. So you can take notes also. But it's all going to be all there, so. So Euclid, you know all about Euclidean field theory measures. They are realized on template distributions or on the other short space, D prime of C infinite function with compact support. And a Gaussian measure is always specified by its covariance. And there's a continuous positive bilinear functional on. So if f is a test function, we introduce a Fourier transform of the measure. And I should say that there's a general theorem which says even if it's not a Gaussian, that you can, if the Fourier transform is a continuous bilinear functional, positive definite bilinear functional, then I should have mentioned somewhere, yes, positive definite bilinear functional, which is continuous, then there is a measure on the dual space of a nuclear space. That's the S prime or D prime and so on. So that goes by the name. I think Prohorov was the first to find this, according to Kolmogorov. But actually it is known as the Minlos, Gross, Sadhanov, etc. theorem. It's a generalization of Buckner's theorem. So I'll consider scalar fields for simplicity, okay? And I'll consider massive scalar fields. Massive scalar fields can also be treated, and mass will be put in as part of the interaction. However, for the computation of certain critical indices, like the susceptibility and so on, it's best to put the mass into the covariance, okay? But I won't be computing really critical indices, and I will just stick to this picture. Now, this picture has been used for a long time, which you, I think, to David, and I used it in year 2000 with Benedetto Scopola, studied the model due to Plantier, and then we found that we can do marvelous things with this. So let me go back. So what is phi in the square brackets? It's supposed to be a dimension of the field. Well, you know the standard definition is d minus 2 by 2, right, of the scalar field. However, there are other possibilities, and I'll consider those later. That is, you can be d minus alpha by 2, where alpha is bigger than 0 and less than or equal to And in this case, you get a generalized free field. In other words, there's a spectral representation for that over a continuum of masses of a standard propagator for a massive free field. And we say it's a generalized free field because the Gaussian version of this leads to, you can compute the commutator function of this. And that's called the Pauli-Jordan function, and advances of space-time distances. Whenever that happens, we call it a generalized. Now, you will notice that this covariance is singular at x equals to y. It's a generalized function distribution. So the ultraviolet cutoff is to get rid of that singularity for the moment. So what we do is this trick, which I'm going to do a specialized form of it because it also leads to other developments. So this singularity, we will do this as follows. Suppose u of x is a smooth, rotationally invariant, positive definite function of compact support. I always say positive definite because you need that to get the covariance to be positive definite. Then this can be achieved as follows. Suppose you take two C-infinite functions of compact support of half the finite range, beyond 1/2 the distance, there's 0. And then you take the convolution. If you take the convolution, that's positive definite because the convolution, and you can calculate the Fourier transform of the convolution, is g hat, that's positive. And as far as positive definiteness is concerned, it's enough to prove the Fourier transform is non-negative, okay? Which is done. Now, okay, any questions you can always ask me. It's supposed to be a mini course, so I'm supposed to be able to answer questions. So then we observe that simply by scaling, u is rotationally invariant. So you think of it as a function of b, okay, which is x minus y squared divided by L squared. Well, you can scale in L. If you scale in L, then you up to a constant, which Malik knows how to compute, 2 powers and so on and so forth, you get back x minus y to phi. In fact, that's a mistake. It should be a square bracket in that phi. That's the dimension, okay? Now, so we define a sequence of cutoffs. L is any number, real number bigger than 1. And this is a sequence of cutoffs. Then we see that these cutoffs go to 0 as n tends to infinity. So we will define the cutoff covariance by just cutting off the endpoint. You don't have to write this down, you know all about it, David.
That's true, but I like writing things down because it makes me think about what you say.
Yes, and then promptly forget. Okay, so that's clear. So I'm cutting off the endpoint, which is epsilon n. And now, because u is C infinite, C epsilon n is C infinite. U is positive definite, so C epsilon n is positive definite. So we have what we need. It's also of compact support. Okay, so there's a theorem which says, which is very easy to prove in this case, that if the covariance has a certain degree of differentiability, then the sample parts of the measure have that degree of differentiability. I mean, you can prove that by just computing covariance. You think of a Savoliev norm of high degree, or a small set, and take 2 of them, squared, 2 of them, and then you will get something, and which is finite. And then you will see that Savoliev norm squared is positive. It's a positive object, and so the random variable almost everywhere is bigger than 0, and then for some volumes embedding, you can prove the rest. Okay, that's one way. Okay, so we define also scale transformation. So this is the way it goes. The scale, you all know about the scale transformation. I think Antti defined it, and this is the way. On functions, that's on fields, it goes like that, but remember the covariance has two fields in it. That's why it has two phi, twice the dimension. Okay? And on functional fields, this is the definition. So with these definitions, the scale transformation form a multiplicative field. Going too fast? No. Sorry. Okay. I also defined a unit cutoff covariance. It's an analog of the unit lattice. Okay? Where I put 1 at the endpoint. And then you can see, observing the scaling relation and the formula that I gave, that the C epsilon n is equal to S, is the scale transformation of the unit cutoff. Okay? So we now define, you have an integral of 1 to infinity. You can split up the integral from 1 to infinity from 1 to L to L squared to L cubed, union of all these half disjoint intervals, okay? So this is clearly smooth, positive definition, a definite of range L to the L, range L. Why? Because if x minus y is bigger than L, the little l goes up to capital L, then x minus y divided by little l will vanish, okay? Because it's compact support 1. Okay, so it's that's compact. So from this, by iterating, you can get so C can be written as from the scale covariance of the unit thing and the fluctuating covariance. It's the sum of two things. And now you can iterate this transformation. If I iterate this transformation, I get C as the sum of these fluctuation covariances, and each fluctuation covariance, because I rescale, reads like that, okay? And these are all positive definition functions, same infinite function of range L to the n plus 1, okay? The gamma n's. So they have an increasing range of supports. Yeah. Okay. Shall I proceed? All right, David?
Mm-hmm.
Familiar?
You have to look at somebody else besides
Yes.
me. I do know.
Yes.
So. You have to
All right,
look at
Susanna.
Medina.
Martina, all right, or Medina, yes. Yeah. Okay. Okay, this gives a so-called finite range decomposition. And it's extremely helpful when you do study Wilson's renormalization group, at least for a certain class of models. Because in the old days, it simplifies the analysis of the fluctuation integration, which is the integration which you'll see presently. And secondly, you don't have to do cluster expansions to study that partial integration anymore. So we have a family of independent Gaussian random fields, okay, corresponding to these covariances, gamma n, and you can write phi as a sum. Okay. Actually, for most of this lecture, it's enough. I don't need compact support. I need only that you be rapidly decreasing, that's all, you know, Schwarz function. So these fields are smooth, and they vary slowly over length scales L to the n, the zeta n. And you can do a Chebyshev inequality on that to see this. And that if x minus y is less than or equal to L to the n, this, because you can estimate that with the squares, and then you calculate the covariance, and that's a derivative, and you calculate the covariance and derivative of the covariance, and the covariance has x minus y divided by L to the n, and when you take a derivative, n to L to the n, 1 upon L to the n, which is squared when I do the estimate, which is L to the 2n. Okay? So that works out fine. So this is the slow. Now, I should mention something which I won't have time to deal with at the moment, with the hierarchical models. So Galavotti's interpretation of the hierarchical model is a hierarchical renormalization group that is replace fields on length scale L to the n by piecewise constant. Replace the field by piecewise constant, so that it's constant on L to the n, and you choose blocks of size L to the n. And that gives actually a clear hierarchical structure in the end. Okay, so since the zetas are just a sum, infinite sum of independent fields, we can calculate by integrating out the fluctuation fields step by step, okay? So now I'm going to discuss, this can be considered as an iteration of a single normalization group transformation whose properties I'm going to discuss now. So if capital F is a function of the fields, we'll define a renormalization group transformation, which I give. It consists of two steps. One is a convolution with F and a scale transformation. Scaling is very important to achieve non-trivial fixed points. Otherwise, you'll never get there without scaling. So this is the definition, okay? So you take convolution and then rescale the field at the end. Now, what are its properties? It's a semi-group property. That's the first thing. These transformations form a semi-group. And to prove this, we must see how scaling commutes with convolution with a measure. I'm doing this discretely. It's probably easier if you do it continuously, but we're doing discretely. So we have this following property, that if you take the convolution of a scaled function, that is the same as taking the convolution with respect to a scaled covariance and then acting with the scaling at the end. This can be proved. I think I'll give a proof of this. It's quite elementary, okay? So zeta is a Gaussian random field with covariance gamma L. Then the Gaussian field SL zeta is distributed according to the scale covariance. Now the left-hand side of this equation, okay, is just the integral of that, and that is of the scale with respect to, and by the previous observation, this is the same as the integral of zeta with respect to scaling field, but with the rescale covariance. Now you can check the semigroup property. It's a semigroup because you can act now. By definition, it's SLN to the n, mu gamma L to the n, that's it. That's a beginning convolution, and that's equal to SL to the n. I can take it out, and provided I change the covariance, and then I use the group property of the scaling transformation, and then I use the fact that these two together is the addition of gamma, because it's a product of, it's convolution of two measures, Gaussian measure. It's the sum of two, okay? L to the n plus, and that is the same thing as gamma Ln plus 1, and now it's rescaled back and you get T Ln plus 1. So that's the proof why we have this semigroup. Okay? Any questions? Now, TL has a unique invariant measure. And what is this invariant measure? It's just mu c, remember, the unit cutoff covariance, C. Maybe I should have put in an index C1 or something. And to understand that, it's very simple. You see, you act on, you integrate TLF with the d mu c. That's the same as SL by what we have shown, mu gamma L by definition, and that's the same as that, and then that's back to d mu c. Okay? So TL is also a contraction semigroup. So on LP, and it's very easy to prove because it's a convolution measure, okay? So if you do this, the pth power of the LP norm, that's the same as computing that. Write it out, the definition. You use Hurler's inequality, and you will get that. Okay? What about that? Yes? And then use the fact that this is nothing but the TL of F, and it's an invariant measure, so it's that, okay, FP, and that's the beta. Now this is a general fact, that whenever you have processed anything with an invariant measure, you can prove LP properties with respect to the invariant measure. So I'm allowed to find a Wick monomial. And here, you know, these are Hermite polynomials, but Hermite monomials. And I'm going to use a trick to my friend David, which is very slick. So we first defined a second functional derivative of f. So what does that mean? That means that, let's say, the second derivative of f at phi, and then the two phi's, means that I'm taking Gateau derivatives, if you wish, at the point phi, in the direction phi phi. If I compute that, it really amounts to the same, C of the covariance C and functional derivative with respect to phi of x and derivative with respect to phi of y. That's what it is. It's a, okay?
Maybe you have to use a different phi in the first formula?
Sorry?
Yeah, I think maybe you do have to use a different phi, because on the left-hand side, what is it a function of? The Laplace in C of f. And,
yes, you're right. I should use a different phi.
Right, put a prime on the second and third.
I will change it eventually. Thank you very much.
Maybe we should write it on the blackboard here, then people can see what we mean.
This is magic keyboard.
Do you want me to write it, Pronob?
I can think I can do it. Okay.
It's the primes are the, on
Integration.
the second,
No,
the primes are on the second two phi's.
I'm integrating with this little phi prime in.
Yeah, but you want the f to be a function of phi semicolon phi prime phi prime.
You mean this is not a phi prime? Why not?
That's a phi.
I'm calling phi a phi prime here. Okay.
Let's have a vote on it.
Alright.
If you do like this, it will always be a second order polynomial. Cannot be, no? Because
If I
you
compute
prime.
this,
I agree with David.
I think you should put the prime
Integrate
There
the
and there.
derivatives.
oh yes, yes, and I'm integrating, you're completely right.
Yeah.
I'm integrating all those phi prime at the point phi.
Right.
That's clear, I'm sorry, yes. All right. You're completely right, no. This is a fantastic blackboard.
Yeah.
Okay, you're completely right. Where am I? No, I'm going in the wrong direction. Okay, I have to change that, okay? Let me done, because I'm integrating all the files, okay? It's clear. Okay, now,
So this is just a kind of fairly rigorous way of writing
yes,
what
that's
you
right.
had.
To make it really rigorous, you should define the Banach space on which you're defining, you know, etc. But this is it. Okay, so if you take, everything is well defined because I'm working with smooth fields with unit cutoff, okay? That's that. So I can define locally a polynomial, local monomial, m fields with m derivatives. Okay? And then I define the Wick product, this is due to David British.
I don't think I'm the inventor of it, but I
But
just
it-
like.
I learned this from you, actually. As equal to e to the minus half. Remember, I'll say why. Because when you do the renormalisation group transformation, the convolution integral is a heat condom. So that has a plus, okay? And then the scaling at the end. We should work it out. So e to the minus half, okay? That's a definition. And from this you can derive all the properties. All right?
So the exponential is defined by expanding the
Expansion. Expansion is defined because it's a PNM is a finite degree, okay? So to stop, and it'll put in a lot of C's, okay? At the same point. So the main statement is that Wick monomials are eigenfunctions of TL. This is another way of looking at Wick monomials, okay? Which is very useful because why? So we define over some volume X, capital X, this object. And the theorem is the TL acting on Pn of X is L to the d minus m phi minus n of that with a rescaled volume. In infinite volume, of course, it would be a true eigenfunction. But then we would have to have some decreased properties and so on and so forth. Nevertheless, it's very useful. Why is this the case? So TL can be written as SL acting on the heat operator, functional heat operator on F. It's a convolution. So now TL on the Wick ordering at that is the final scaling is there. Inside you have those two objects, e to the half delta gamma minus half delta C. Sorry? Is it correct? Now you can combine the two exponentials and you will get delta minus C minus gamma L. Always keep in mind that I have this integral 1 to L, L to L squared, and so on. Okay, so these are easy to calculate. So this is equal to, I don't know why there's minus signs floating around. I mean, there's no minus there. Okay, the subscript of the functional Laplacian has no minus. Okay, I mean, maybe I didn't put a backslash or something. SL, see, that's what it is. That is SL of the function computed at it's a Wick ordering SLC by definition. And now if you compare both sides, and that is equal to the same, you can do this as with C, and you can't, dimension of F is a total dimension of F. That is the dimension of the fields and the sum of the dimensions of the fields and of derivatives of fields, which constitute together.
And maybe we better write that down.
What?
The
dimension of F is?
Yeah.
Yeah.
Should I write it?
You want to write it down? Dimension of F is what I had written out earlier. Yeah, that's the dimension of F.
Oh, okay.
Excellent. All right.
Yes, okay.
So a correction has to be done in this formula here. Is there how do I point this? Oh, you do that.
Let's see, it should be
There's a pointer.
it's this little guy right there.
Okay, there's no more signs left. You see,
There.
this should not be there.
That
This
minus sign.
This minus sign should not be there. Okay. This is a typing error. So that's a proof. Now we classify this. These are all around the Gaussian part. So because mu c is in the embedded measure is corresponds to the Gaussian measure. Okay, and relevant, contracting, irrelevant, or central. Okay, depending on the exponent. Central is the most difficult case. But relevant or irrelevant. So the exponent, when the exponent is positive, we say it's an expanding variable. When it's negative, it's a contracting variable. And when it's zero, then it's what's supposedly called central. So it's all part of the stable manifold theorem. There's a center. You can also have a center. I think. Okay, I'll discuss this later. So, how do we remove ultraviolet cutoff? So we take a torus of side length r. Okay? And we define the partition function with the cutoff covariance, C epsilon L, and I put in some xi tilde of n, g tilde of n. And V naught in general is, I take it as a quadratic and a quartic perturbation. So it has a grad phi squared, it has a phi mass and g naught. So mass is now, for my purposes, part of that. Okay, this is sufficient for proving things. Now, okay, I should spend a little bit of time with this. So by dimensional analysis, you can show that there are dimensionless parameters, z, xi, mu, okay, such that xi tilde n is that, g tilde n is that, and mu tilde n is that. Think of epsilon n as L to the minus n, okay? That's what it is, L to the minus n. So 4, 5 is 4 in the conventional d minus 2 by 2 if you take phi, the scaling dimension phi. It's 2 twice d minus d. Let's work it out. What happens?
Or you want maybe further down when it comes on. Is the C, that's in front of the gradient phi squared? What
Yes,
was it?
yes, yes. That's right. In general, that can evolve, and we see that it does evolve. So let me concentrate on G tilde. So G tilde and 4, 5 minus D this is D minus 2 by 2. And if you take an inverse, that's G tilde n, okay? And you can see that something is wrong.
Because you're not getting the same as on your screen, you mean?
What am I doing here? 4, 5, that's correct. L to the minus that, L to the minus that, okay? It should be L to the plus, so.
So you put in the canonical.
Yes, I put in the canonical, that's all right. Oh, yes, it's all right. It's okay. It's okay. So take d equal to 3, which interests a lot of people have. I'm working, if you let g tilde n, then g tilde n, d equal to 3. Then g tilde n and take epsilon n L to the minus n, okay? Then g tilde n L, well, first of all, it's 4 minus d. And this is g tilde n, okay? Times g. So suppose you take d equal to 3, then this is equal to n. 3 is L to the N. I don't write very well, I'm sorry. Okay, L to the NG. Okay. Now there are various possibilities open. If you want to take a scaling limit, you have to parameterize in terms of dimensionless objects. And if you parameterize in terms of dimensionless object, the dimensional full object, which is what appeared originally, tends to infinity. The bare coupling goes to infinity. In Wilson's framework, the bare coupling goes to infinity. Okay? And G, the renormalized coupling or whatever you want to call it, is the dimensional thing. If you're lucky, it hits a fixed point, either Gaussian or non-trivial, okay? That's the way. The other alternative is to not do that, is to keep G tilde N fixed. Okay? Then divided by L to the N, that's going to 0. That's a super renormalizable case, ND3. Okay? You can make the same analysis for the mu's and the xi's. Now, this is a very good reference for this, for the super renormalizable case. Circa 19. So
92 or something like
Huh?
that. I think it's like 90.
I'll put in the reference. There's a paper of Bridges, Dimick, and Hurd where they analyze the super renormalizable case using the renormalization group. And they prove the existence of the Gaussian limit and so on and so forth there. It's not a full study in the sense that they don't prove all the axioms, the cutoff scheme breaks the OS positivity, etc. Okay? But it gives you an idea, and the analysis over there can be much simplified by using this finite rate method. A lot of the stuff there, you don't have to do it that way. But I'll put in the reference. Okay, now. Now, so this is what we had, and we put in those in terms of these dimensionless objects, G mu, xi G mu, and then you get a huge volume. It's a scale volume, the same thing, out of the scaling of the fields, and because each field has argument x divided by L, right? And when you work this out, x divided by L to the n, and it becomes a huge volume, L to the n, r by 2. You can take r equal to 1 as far as I'm concerned. Yeah. Okay? Lambda n. So the analysis now is to prove for the ultraviolet cutoff removal in the sense of Wilson to achieve a scaling limit is to analyze that z of lambda n. Okay? That's the idea. Infinite volume. Okay? How should we do that? Okay. What are these RG iterations? Why is that?
To go back to full screen.
Huh?
Yeah, you have to go back to full screen, otherwise you will not work properly. Maybe you get away from full screen at some point.
Perhaps we can do it.
No, I think you have to do on the computer.
We have to do it on the computer. Okay.
The last one.
Where is it?
This is the last one.
It's the last one. Enter full screen.
That's better.
Here's your,
Okay.
here's your, this thing.
Okay, so there's a scale-by-scale analysis we have to do. And so this is what it is. And then you have, I mean, this can also be done for correlation function. I'll show you later on what happens to get the scaling fields. This, it's because it's an invariant measure, so I can put in capital TL, right there. And then it's a new function of the fields, it's action. And it, because of the scaling, it's in a smaller volume. So this leads to the definition Z1 lambda n minus 1 is TL of that. Now we can proceed. We can iterate this transformation. And just a simple iteration of what I've done before. And after capital N iterations, you will reach something on a unit block or a block of finite size. No capital N dependence. And now we have to take the n tending to infinity limit to control the infinite sequence of iterations. That's a job. Now, remember V0, capital V0 was local. It had the factorization properties on the function. It's an integral of a local function. Okay, so it was a union of, it had factorization for unions of sets with disjoint interiors. But for Z1, there's a non-local part that is corrected. Okay. The whole idea is to extract out a local part from this non-local part and constitute a remainder, okay? And this remainder is going to be the irrelevant term. And the change in the local part is reflected in the change in the parameters, and that's a flow, local flow. So at any given stage, you'll have the irrelevant terms, okay? And you'll have a change of the local flow. So Wilson said that in the end, the irrelevant terms should not matter. The fact that there's a huge non-local part. And the most important intuition is already there in the local flow. That was Wilson's intention. And mathematically, this has been justified. So we have to control the infinite sequence of iterations. And to do that, and later on I'll introduce coordinates, which represent, on the one hand, the local flow, on the other hand, the irrelevant terms. And this is in terms of polymer activities that has been going on for a long time. Okay? And won't be that today. So in other words, set up a Banach space of coordinates, okay, which will be enough to compute correlation functions and prove theorems. So before I do that, I want to do some approximate calculations. I'm making good progress. Very
You want me
soon.
to slow you down?
Very soon I'll be coming to an end. I prepared a certain amount. Okay. So the fastest way of computing is by continuous methods. And the discrete semigroup of the will be replaced now. We take L to be a continuous parameter. You can call it what you want. I prefer to call it L as e to the t. Okay? And t is bigger than or equal to 0. And by abusive notation, I'm writing T st gamma t instead of t exponential t. Okay? So the continuous transformations form a semigroup. I mean, this is easy to see because e to the t times e to the s, e to the t plus s, and that's what it is. Okay?
So maybe that was a bit quick, right? I mean,
Yes.
I think you have to go back to the equation which represented the covariance as an integral over length scales and point out that we could have
Yes.
taken L to be.
Absolutely, in a continuous sphere.
Yeah, so, right, so if I.
This is what's going on. I remember I divided up the integration region as 1 to the L, L to L squared, etc. And I can do that in a continuous way. That's what's going on. 1 to e to the t and e to the t to t and so on. Anyway, so, and TT is a contraction semigroup on L2 d mu c. And the generator is that, LF of the semigroup is that, okay? You have to restrict yourself on the space on which this limit exists. Now, what is the generator? So we define as the nth tangent map at phi along direction f1 to fn, and the functional Laplacian we define, okay, you can easily check that when I look at gamma and the covariance, and as David was saying, L is continuous, right? And evaluate a DDL at 1, then you get gamma dot is U, which is positive definite as C infinite and a compact body. Okay?
Yeah, can we go back to that equation, because not everybody probably remembers it, all the way back to the decomposition.
There we are. So I'm saying you take it L as continuous, capital F. Evaluate it and take the derivative of gamma L at L equal to 1. Okay? And then you can see that all you have is U that's left. U of x minus y.
Yeah, so I mean, the way I would say it is that you're taking L to be 1 plus epsilon, and then the
Okay.
epsilon go to 0.
Yes, that's what I'm
Right.
doing. Okay.
Then you will get a continuous version of the discrete
Yes.
transformations.
Yes.
Please explain.
Okay? That's what it is. Then, I also define a vector field from the scaling, which is t equal to 0 of that object, e to the minus t, acting on its argument, okay, on phi. Then if you do that, then L turns out to be half Laplacian gamma dot, which is u plus chi. Yeah, this is straightforward. So TT is a semigroup, okay, with L as a generator, and if you can write it as e to the TL, consider a function, evolved functionality of phi, TT acting on F, and take the derivative, it reads like that, ddt. Yeah. So, with initial condition F0, it's going to be F. This evolutionary equation becomes a more convenient form, a more familiar form, if you write ft as e to the minus bt, useful for computations. And in which case, you will generate, because L has a functional derivative in it, you will generate the second order Laplacian in it, you will generate this term. Okay? It's the first term plus the second term, linear term and the second term. The linear term is the second order Laplacian, and acting on, plus the scaling acting on V, and the second term comes from the action on e to the minus v of the functional Laplacian. This is what it is.
That's a
Okay.
Hopf-Kohl transformation.
Sorry?
Nowadays, people call it Hopf-Kohl's.
No.
Yeah, Hopf-Kohl transformation. Writing.
Well, anyways, one of the central references is Wilson Kogut. Wilson Kogut has everything. We didn't prove anything, but he has everything in it. Okay. And this equation is there. And this equation has been used quite effectively for perturbative renormalisation, starting with Polchinski in the early 80s. Then I wrote a paper on the nonlinear single model done in a special way, which might interest you. Flow equation, perturbative flow equation. And got back the results of Polyakov, Brazil and company out of that. Then Christoph Popper and Manfred, they worked on it, and they did a very fine job on the Stringer functions and bounds of the Stringer function, which Christoph has developed. There was approach to Yang-Mills, etc. So it's a long history behind it. It's quite effective, actually, for doing formal series expansion and perturbative renormalisation. So, as I said, this is useful for perturbation theory as far as bosons are concerned, for nothing much else. For fermions, we can probably do more, okay? Because when you have cutoffs present, the fermion series converges, Pauli principle. As Cayaniello was the first to see this. Okay. So, considering bosons, and then, okay. So I'm going to do a flow in the second order using this evolutionary fashion. So the idea is, I'm going to do an infinite volume, because as we see, U is a compact, the kernel, U is a compact support, C infinite, right? So I can work for this computation, infinite volume, without any problem. Okay? So I parameterize the effective potential Vt as flowing Zt, Zt, Gt, and mu t. Okay? It satisfies the flow equations. We have to prove now, well, how does Zt, Zt, Gt, and mu t evolve such that the flow equation is satisfied to second order? Okay? We have ignored a 5/6 term. It's in D in bigger than or equal to 4, it's irrelevant. When D equals 3, actually there's a 5/6 term, is marginal, it's there, and it gives the so-called tricritical, it dominates the tricritical point, but ignoring that, okay? Now we will assume that the inductive assumption that Zt and mu t are of order Gt squared. Okay? Now, I just plug in ddt minus the one part of it was, remember it was L, and then we had the rest. Okay, ddt minus L, lambda t, and lambda t and m represent the three coefficients that are there. So acting on that, you get the action on lambda t and the action of L on P and N, which we know what it is d minus, the infinitesimal version of what I had written down earlier. I wrote down L to the power of d minus m minus n, okay? And infinitesimal version of it is that. Then we turn to the nonlinear term in the flow equation. The nonlinear term in the flow equation, and insert in the double integral, okay? Where is that? Yeah, okay. This produces, up to relevant terms, this produces. And then we Wick order it. Double integral of gamma dot xi with these two terms, okay? The phi q. And complete Wick ordering gives this. The well-known coefficients 9, 36, 6. So what do we do now? There's a non-local term in it. Non-local phi-4. This term is a non-local phi-4 term. We're going to localize that and produce in the localization procedure another relevant term. So we can write it as famous, I can write this as half of this, that, okay? It's the same thing. Now, the local part gives a phi-4's contribution, and the last term, essentially there's a derivative, because there's that's like taking the derivative of phi squared, which is phi grad phi, and then squared. This gradient is enough to show that it's irrelevant. The coefficients are well defined because C gamma dot is smooth, and gamma dot is U is a finite range. So the non-local, now the phi squared term is similarly localized. There was another term there, phi x, phi y. We can localize that too. Okay, so as well as the marginal. That's where the xi term evolves. So we get out of this by matching a flow equation to order, a perturbative flow equation. And I've used d minus 2 by 2 as a scaling dimension field, okay, the standard one. And you get for d, gt, mu t, and d xi t. Now you see that this is mu t is a growing variable. It's an expanding variable. It has a positive constant in front of mu t. So we have to deal with that. So as t tends to infinity, for d greater than or equal to 4, well, if d is strictly greater than 4, then it tends to 0 exponentially fast. If d is equal to 4, it still tends to 0, but logarithmically. Power law, sorry, 1 upon t. Okay? So this is the intuition behind the fact that for d greater than or equal to 5, you always have mean field theory Gaussian fixed point. For d equal to 4, you also have a Gaussian fixed point, but a slow approach, a slower approach. This is all this infrared analysis of Jelensky and Kupianin, and later on David and collaborators have done. Okay? So, but the beauty flow will diverge. So in order to get the whole flow fixed, we have to choose the initial conditions properly for beauty. How will we do that? There's a general trick which goes back. Who was the name of the stable manifold theorem? What's his name, David?
Irwin?
Huh? Irwin.
Yeah.
It's already there in Irwin's work, in stable manifold theorem. Which is the fact that you reverse the flow. You reverse the flow, assume the flow is bounded, and then calculate what the initial condition should be. That's it. It's a rigorous version of this around. Okay. So what is it? So I integrate up to time t, and then expressing mu0 as a function of the entire g trajectory up to time t, assume that mu t is uniformly bounded, and take t equals to infinity. This gives a critical mass. You can solve this equation. Okay, up to order t squared. I transfer this to the left, the 2 mu t, then method of variation of parameters, ddt, that, right? You can solve it. And then take t equal to infinity, assume that mu t remains bounded always, and consistently check that. Okay. And that's a critical mass. It's a function of the initial point because GS evolves from the initial point. So that's what's known as a critical mass. Now, integral converges in all cases discussed above. For d greater than 4, this GS has an exponential convergence, and for d equal to 4, it goes like 1 upon s squared, it still converges, okay? So, with this choice of mu naught, we get mu t is that. And this exists for all t, and in fact, for d greater than or equal to 4, it converges to 0. That's it. The mass, actual mass that appears is 0, if you fix the critical mass properly. Now, what about d equal to 3? If you look at the equation for d equal to 3, d equal to 3, it still has a fixed point, but it's not small. Okay? Now, Parisi, if I got a CNRS somewhere?
Equals 3? No, I think, I mean, for the dg by dt equation? looks
Yes.
good to me.
Yes?
I think it's right.
Yes, it's all right. It's all right.
But
GT,
when you
GT
s-
has a fixed point, even at d equal to 3.
Well, yes, but you have to ignore the g cubed t.
Yeah. So people have tried to look at directly at d equal to 3 and some n, large n, and so on. Parisi had a whole program when things were being computed by flow equations. Parisi had a program to compute directly with that, but it was an uncontrolled program. He got some results, but of the critical exponents. So I'm going to do something else.
What was his idea?
What?
What was his idea?
Parisi. Well, just use these flow equations for d equal to 3, right? Your fixed point of order 1.
Presumably he just ignored the g
Yes.
cubed
Yes.
term, right?
Yes.
So,
I think he puts it to correction both. I have to look at Parisi's old paper from the 70s. But most work that has been done for d equal to 3 is the so-called 4 minus epsilon, okay? That is, if you choose d as 4 minus epsilon, then you get epsilon gt. Okay? And then so epsilon is small. And this is Wilson-Fisher. Epsilon is small. And then you get the exponent eta as 1 upon 54. You get the exponent, the energy exponent, phi squared, right? I forget what it is, order epsilon contribution, and so on. So these things have been done by Brazaz in his time. I've computed in 1973 some of these exponents. Okay. So that's the story. So can we do anything else which has a chance of surviving non-perturbatively? The answer is yes, and this is fractional business. Didn't I put it down? Oh, yes. So we take now this dimension phi to be d minus alpha by 2. And alpha is now less than 2. Now this, Dyson wrote a paper on long-range ferromagnets in one dimension. And this was then generalized. A lot of properties were proved actually for Galavotti and Miracolo-Sole and then Dyson, okay? And this was generalized in a higher dimension by Eisenman and Fernandez. And Eisenman and Fernandez proved that so long d is less than or equal to 4, okay, d equal to 4 is a critical case. You can, the critical dimension, this is the dimension, in statistical physics, there's a notion of critical dimension. And below the critical dimension, you expect non-trivial behavior. Above and equal to the critical dimension, you want to get mean field behavior, okay? That is Gaussian behavior with corrections. And Gaussian behavior actually no logarithmic corrections for d bigger than or equal to pi. So if you exclude that point for alpha, you'll find that for d, you can introduce a parameter epsilon, which is 2 alpha minus d. Now, long ago, with David, I wrote a paper, okay, and Benedicto, right? And I wrote a paper on, rigorously, on d equal to 3 and alpha is 3 plus epsilon by 2. The flow equations are now changing. You have epsilon gt, you can show. A, g, these are different days, a gt squared, b gt squared, d mu t, wherever it was 2 is now replaced by alpha, okay? And psi t is that. And now we can construct the critical mass. The critical mass is exactly as before. That is, integrate back.
Maybe I could comment here, because maybe not everybody realizes, but the problem before was we wanted to ignore the GQ term. We don't know how to do that if G is going to be of order 1
Yes.
if you solve the first
That
two
was the
terms.
problem.
Now with the alpha, if you can back up a sec. Can you back
Yes.
up? With the alpha in there, instead of in the dg by dt equation, there's an epsilon instead of, what was it there for, 0, right? Yeah, no, 1.
d minus 4.
There's an
4 minus
epsilon.
d, yes.
So what that means now is if you just solve the first, if you just look for the fixed point of the first
It's
equation,
exponential
looking at the
pass.
first two terms, it
Yes.
says gt is of order epsilon, which gives you a better reason to just ignore the GQ term, which is what it's going to do. Right.
So this has been controlled with this cut off in the continuum by David, myself in 2003, I think there's a paper by CNP, and Benedicto. And Abdissalam then came along, he found a little error in our paper, which he corrected, and then he proved the existence of, you see, this fixed point is just stable in Wilson's sense, that physicists would call it infrared stable, but it's stable. You're approaching it very fast, exponentially. But the Gaussian fixed point, there is a Gaussian fixed point by putting g equal to 0, okay? That's unstable. The Gaussian fixed point is unstable. So our friend Malek proved the existence of a trajectory for sufficiently small stable fixed point, a trajectory which links the two fixed points. It's a beautiful paper actually in CNP. Some years later, 2003, maybe 2008 or something like that. He wrote. He's a smart man. So in this case now, I'm back here. There's a critical mass, exactly as before. And this is the critical trajectory. And you can see that as t tends to infinity, this now converges to something non-trivial, which is mu star, which terrorism, of order epsilon, order g star squared. G star is of order epsilon. This is of order epsilon squared. Okay, so this is the approximate flow. So my plan is now, I don't know whether. Okay, so all this has been done. And since then, critical exponents have been calculated by Gordon and his collaborators, right? By taking the massive theory. The massive case in the propagator, because they're interested in the susceptibility, it cannot be done by what I said. Okay? You do it on a lattice, but in the lattice exists finite range decomposition due to David, his student Guardani, and me, and Roland Gaussian and so on. And so you can use that, and that works with mass. And that works also, as I showed, with for fractional covariances. Okay? And so you can use that because you can use a spectral representation again, all over again. You don't need so a lot of work has been done. I'll cite some references. I haven't compiled all the references yet, but I will. So this is a plan. I think I'll stop here. I don't want to go to the next. I've got some kind of a master file for taking things along, and in the end, from this master file, I'll get rid of some things. It is a lot. It has lattice and so on and so forth in the master file. Okay, so this is the plan. So my next plan is how do you analyze? That's quite nice actually. I have 2 lectures left to do the non-trivial stuff. Okay, how do you approach this problem rigorously, and what can you prove? Okay, I think I'll stop here. I'll stop here because I have a lot of frames, but I don't want to show you 247 frames. Okay? But it's very good. I mean, I wasn't too fast, was I?
We appreciate it.
I wasn't too fast. And you had enough time to look at the stuff. All right? So I'll continue with this thing, not more than 8 lines in a frame, at the cost of increasing the number of frames. Okay, that's it. Thank you.
So, are there questions which haven't been
Yes.
asked already?
Yeah, I have a question.
Tell me.
So if you go back when you derive the flow equation, before
Yes.
you derive the flow equation, and there are these, no, 2 pages forward. No, forward, not backward. Not forward. Like 50, page 50, I think.
This,
No, forward.
forward.
Yeah,
Page 50.
page 50, maybe.
56.
Next one, sorry, okay, it is not 50. Maybe 51, I just approximate. This is first order approximation. Second order, yeah, that's the right order. So, because how you can say this phi cube, phi 6 term does not count? Now, I understand the philosophy, okay, but okay, phi, if I look at this phi,
Then I would have to
phi
write
6
down the flow
term,
for phi 6. But actually, the way you deal with this phi 6 terms is that you keep the flow in the shape of the second order flow, but you change coefficients, of course. And all phi 6 terms are in the denominator, in the polymer activities. I will explain that.
yeah, but there are so many, I mean, they come from the exponent, so they are anyway.
Actually, they won't, I mean, there's a way of doing the, extracting the exponents, which,
But are you asking why it's irrelevant, or are you
No, I'm asking how
you
you can control that it's not blowing up. Because
Ah.
you have only phi 4, and then this is phi 6.
You don't have to put it in the exponent.
no, that's the point.
Yeah, but okay, you can
It's-
do
it's
whatever
put-
you want, but then
it's-
if he wants to
It's
be an
put in somewhere,
exponent.
it's put in somewhere, but not in the exponent.
It's-
Yeah, no, I understand, but there is not only this one, there are all its companions
Yes,
which
yeah.
make maybe an
That is why the
exponent.
flow,
The answer's still the same, you
Okay.
don't put them in the exponent.
okay, so the philosophy is this, I will discuss it. The sum of all the irrelevant terms, which do contribute in the next step in the discrete flow to the flow equations of the local part, right? You treat it as a whole. You know it's order GQ, you have to have some norms
Yeah.
and make sure that that's.
No, I understand how you do it, because, okay, I understand, but if you look at the flow, since you started
No,
from
of
the
course,
flow
this-
equation.
This
no?
is.
From the flow equation, this is a nightmare, because in the flow equation, you only see the V, so the exponent,
yeah.
there is no way
Yes.
to put things down there.
Yes,
So, yeah, when you think about how you would go to control this flow equation
Ah,
rigorously.
well, okay, so that's, right.
that's another problem.
But this is not an infinite dimensional problem. No, you will have
No.
the same problem in
So I go to five,
It's
six.
by that dimension.
Must be,
for
yeah.
an ODE.
I will go to 5/6, then I can develop also 5/6, the same way. But then it doesn't end, there's 5/8,
Yeah,
But-
it's,
you know.
Well, that's an interesting problem, how to really control this flow equation.
Yes, we don't know how to do it for bosonic field theories, as far as I know.
How the solution looks like at big field.
Right,
Nobody knows how the
Martin?
nobody knows how the solution.
Nobody knows
How
how.
the potential looks like at big field.
Well,
Okay.
I do.
You do?
I think in your norms it's actually absolutely
You're like the
I
Japanese.
don't wanna show off, but I think we do know what it looks like in large field. But anyway.
No,
never
I
mind.
think I know too, but I know too, because now I have this formula for 543, which control large fields also. But so, okay, I cannot still rephrase in the term of the equation. But, yeah, I wanted to understand if it was. So how so you can control the large field with
So-
the.
In the flow equation for the effective potential, I don't believe you, David.
There's a good guess as to what the effective action looks like at the large field.
Okay.
Yeah, we can discuss that.
Yeah.
Okay, love to learn from you. Okay, so, any more questions? This is interesting what you say.
Anybody who
You're
wants
not
to-
like the Japanese researcher at the CNRS who said, can you do this? It's I've solved it. I've proved the Riemann
I
hypothesis.
haven't proved
Proved
anything. but I
proved the
think it's a
Riemann
good
hypothesis.
guess. No, but anyway, if anybody, well, I can't do it now, but if anybody wants to,
Lunch.
later, after lunch or something,
Okay,
we can discuss this.
so how do I get out of this?
You have to turn off the.
Yes.
So I'm starting.
Yeah, I don't know, I have a phone, I should have. I have a phone, it's not